So I am very excited to introduce you to Dr. Erin LeDell. So Dr. Erin LeDell is the Chief Machine Learning Scientist at H2O AI, the company that produces the open source distributed machine learning platform, H2O. At H2O AI, she leads the H2O AutoML project, and her current research focus is automated machine learning. Before joining H2O AI, she was the principal data scientist at Wise.io, which was acquired by GE, and Marvin Mobile Security. The founder of Data Scientific Inc. and a software engineer. So she wears multiple hats. She is also the founder of the Women in Machine Learning and Data Science organization and co-founder of Our Ladies Global. Erin received her PhD in biostatistics with a designated emphasis in computational science and engineering from University of California, Berkeley, and has a BS and MA in mathematics. Without further ado, Erin, the floor is yours.
Okay, thank you, Kim. I'm going to share my screen. Okay, so I'll try to leave like a few minutes for questions at the end, maybe like 5 minutes for questions. So I won't have the chat window up. So if I don't see your question, that's why. So thanks for inviting me. I'm a little sad not to be in Minnesota right now because I thought I was gonna have a trip to Minnesota this week right after my USAR trip, which was supposed to be last week. So I'll just have to come visit another time. But thanks again for just having this conference anyway. It's been fun to do virtual conferences lately. So my talk today is about automatic machine learning in R, and specifically I'm going to talk about how do we do that with the H2O package. Okay, so this is just an overview. So I'm going to tell you a little bit about the H2O library, and then I'm going to tell you a little bit about what is automatic machine learning or AutoML. And then I'll move on to like how do we do AutoML in H2O, and then just leave you with a few resources and links to tutorials and things like that that you can do later at home. Okay, so first, I guess I don't really have a good sense for how many people in this room here have used H2O or know about H2O, but I'll try to give you a quick overview. So one of the things that I like to do is sort of give people a reference point. So if you're used to other libraries like the Carrot library or the Tidy Models library, it's kind of the same idea where we have a number of different algorithms. And we have a common interface to all those algorithms, and then hopefully you don't have to use a whole bunch of other tools when you're using H2O, because we try to provide like everything that you would need to do machine learning. But some of the sort of distinct characteristics of H2O as compared to some other libraries is one is the algorithms themselves are distributed. So we have both multi-core and multi-node implementations of these algorithms. So you could run them on your laptop where it's all parallelized across all the cores on your laptop, or you can actually run it on an actual cluster of multiple machines. The algorithms are written in Java, but as data scientists, we're more like R and Python type folks. So we have an R API, which I'll be talking about today, but we also have an API in Python and Scala and a web interface as well. So one of the ideas with H2O is that you're able to write code in a language that like you're familiar with, like R or Python, but then you're able to productionize the models easily by exporting them either as pure Java code, or we have a couple different other formats that you can use to productionize the models. And I'm not sure how many people are using Hadoop and Spark these days. I know that at least Spark is still quite popular, but if you are, there's like a good integration with those libraries. But for the most part, people are just using it as a, just a normal R package on their laptop. So this is just a little bit more detail. So I mentioned already that H2O has a bunch of machine learning algorithms. So we have supervised and unsupervised algorithms. And we try to have all the popular ones that people like to use, like gradient boosting machines or random forests. We have deep neural networks, GLM. We have a wrapper for XGBoost, which is a popular GBM library. So there's a number of other ones that I won't list, but you can visit our user guide that has the whole list on there. And then another thing that we tend to do with the H2O library is we try to do anything sort of automatically that is code that you would typically have to write over and over again. So one of those things is like how to do basic data pre-processing before you do machine learning. So some algorithms require that you fill in missing values. So that's something we do automatically. If you need to normalize or standardize the variables, we do that automatically. If you need to do any kind of categorical encoding to use an algorithm, we will do that automatically as well. And then another thing that is helpful is we have what we call automatic early stopping, which is just kind of a built-in way to not overfit the models. And this is more important on things like a GBM and deep neural nets, where it is quite easy to overfit. And so we have some just, default check, how do I describe it? Like a default mechanism for checking to make sure the validation error is not, starting to go up, because that's when you would start to overfit. So that makes it a little bit easier to use. And then we have other things like cross-validation. That's quite easy to use. You just say n folds equals 5 or something like that in the function itself, and it will do cross-validation. We have grid search and random search. And then once you have the models, all the models have variable importance and model evaluation metrics like AUC, MSE, log loss, that type of thing. And then we have a number of different plots. So we try to get you pretty far, like in the data science pipeline. There's probably, other things that we could include that we don't include, but this is pretty much the standard of what you would need to do in a data science pipeline. So that's kind of an overview. And okay, so yeah, feel free to ask me any questions about that at the end. And I can also point you to more resources, because it was a pretty brief overview. Okay, so for AutoML, one of the things that I like to do is talk about, it's hard to define what is AutoML, because there's not like, it's not a word in the dictionary you can look up, and I don't even think there's a Wikipedia page for it at this point. But so a lot of people might agree or disagree about the definition. So I just like to talk about what are some of the goals or features of AutoML. So one of the things I think is sort of the defining feature of AutoML is like the goal is kind of to train the best model that you can within the least amount of time. And by that I mean time with respect to the amount of time that you're writing code to make that all happen. That could include, if you're writing code manually, like a bunch of grid searches, trying out a bunch of algorithms, evaluating the algorithms, comparing them against each other, all of that type of code, we can just reduce into one function. So that's really reducing the amount of time it takes just to set it up. And then once you're actually running the model, we try to do something efficient so that you find a good model quickly, and you're not, waiting for 5 days to, do a giant grid search and finally get the best model. So we try to make it like, not wasting your time on either end of that spectrum. So, this is kind of reiterating my first point, but like one of the goals is to reduce the human effort to train good machine learning models. And because we make it so simple by having, I guess one of the defining characteristics of an AutoML tool is like, it's really just one function, and all you should have to do is tell it what your data is and what you're trying to predict. And maybe, if most tools have a way of saying like, which metric do you care about? Like, is it AUC you're trying to maximize? Are you trying to minimize MSE, or, some way to specify your desired metric. But most of them have defaults for that as well. and then how long do you want it to run? Like how much effort do you want to put into it? So that's kind of like what an AutoML interface looks like. So with that said, like that means that you don't have to think about, you know, what algorithms are being used, or what hyperparameters you need to look at or tune, and what values you need to look at. So it's just a whole bunch of expertise that you don't actually need anymore to train models and do machine learning. So, and even if you're very good at like one algorithm, like maybe you're really good at GBMs or something like that, but you don't know anything about deep learning or anything about, I don't know, maybe you're good at one type of GBM, but you don't know the XGBoost GBM or something like that. So it just really, you know, lets you have a lot more coverage to what you can try, and with whatever knowledge you come with. And then another goal would be just overall, we want to just improve the performance of the models that you would be training. So we try to, I don't know what the metric is, but like we try to do better than like the average data scientist. Like hopefully, you know, you would be able to get something better than that. And then another thing that's useful is AutoML tools can be used like in scientific applications if you're some kind of researcher, and you know, maybe AutoML or maybe machine learning isn't your main skill set, but you're just trying to use it in your research. I see AutoML tools as a way to help in those cases as well. And it gives you like a really easy, reproducible baseline for any problem. So you can always start there and then, you know, try your hardest to beat the AutoML, or, you know, look at the results and see what you've learned from what you see there and then improve upon that. Okay, so okay, so let's talk about like different aspects of automatic machine learning. So this is really just aspects of machine learning in general, and the ensemble piece at the end is, I would say, optional, but if you remember, the first point is to train the best model in the least amount of time. Generally that if you utilize ensembles, you're going to get better models. So depends on what your goals are. If you want something, you know, more lightweight or more interpretable, you might choose not to use ensembles. But if your goal is just model performance, that's the way to go for sure. So here's a couple more, you know, points on each of those categories. So for data pre-processing, that's just stuff that I've already talked about, like how do you, you know, deal with messy data if there's missing values, if it's, you know, you have categorical columns, how do you deal with that? That could also include things like feature selection or feature extraction. Like if you have a very wide data set, you might want to do some of that. And then one really important point that maybe people don't realize is so important is how do you treat your categorical variables? Because I think this is one of the things that you can gain the most performance if you do this right, even more so than like switching to different algorithms. I think this is, you know, the way that information is encoded is like super delicate, and each algorithm can use that information differently. So this is especially important if you have high cardinality categoricals, like if you have some, you know, some variable in your data set, like zip code, for example. There's like 40,000 zip codes. And so if you're, you know, not careful about that, that could just blow up your algorithm. You know, if it's trying to do one hot encoding, you have 40,000 extra columns, or, you know, something like that. It's just important to, you know, if you have nice clean data, maybe no categoricals, this type of thing doesn't matter, but it makes a big difference. So then in terms of model generation, the things that people are most familiar with probably are like grid search or random search, where you just try a whole bunch of things and see what happens. And by that, I mean, try a whole bunch of different hyperparameter values for each of your algorithms. There's another technique called Bayesian hyperparameter optimization, which is a little bit more sophisticated, but it's something that you can't do in parallel. You have to do it in a sequence of steps. And so it kind of gets you closer and closer to the right model each time by building sort of a mapping between the hyperparameter space and the outcome, which is like if you're trying to maximize AUC, you kind of build this function between the space of hyperparameter values and that. And then, yeah, I'm not going to go into a lot of detail because we don't have time, but just know there's a lot of different things that people use to kind of generate models and to tune models. And then lastly, something I always like to do is do ensembles at the end. So if you have a bunch of models, then one thing you can do is just ensemble them together, and there's a different techniques. So the one that I use the most is called stacking, or super learning, or stacked ensembles. It's all the same thing, it's just different names for that. And that's a technique of actually learning through machine learning what the best combination of the models is. And then lastly is ensemble selection, is just another type of ensemble technique that seems to do pretty well and people like. That one I think works a little bit better if you pair it with models generated from Bayesian hyperparameter optimization. I won't go into details on that, but you know, there's not like one best method here. It all kind of depends on what goes into the ensemble. And so it's hard to say what is best to do in advance. Okay, so regarding AutoML, so I guess the goal in going through all of those points is like, those are all the things that we would have to automate to make this work. So that is kind of the point of those last slides. So this next slide is really just to point you to a reference that I think is useful if you're new to AutoML, which is, there's a blog post that I wrote that's kind of details the different techniques used in AutoML. So namely, it really depends on like, what is your data type? So if you have image data and you're doing image classification, that's like a whole different category of AutoML. If you have text data, that's a whole different thing. If you have tabular data, that's like what I'm going to talk about today. So that's a whole different type of thing as well. So anything with image data or text data is generally going to be in like the deep learning, very complex deep learning category. And what you're going to do there is something called neural architecture search. And that's not what I'm going to talk about, but you should just know that when people talk about AutoML, they could be referring to a lot of different things. And this blog post kind of details that and gives some examples of different packages that you can use for different data types. Okay, so next I'm going to talk about H2O AutoML. So how do we do this in H2O? So this is that last slide that I had, but I'm highlighting the things that we specifically do in H2O AutoML. And all the things that I've listed on here, well, maybe not all of them, but some of the other techniques, like there are other AutoML tools that use Bayesian hyperparameter optimization. There's other ones that use genetic algorithms. So there's lots of different approaches to this. And so I'm just going to talk about our approach, which is a combination of random search and stacked ensembles. And we do like a little bit of data pre-processing. One of the things that we're working on right now is automatic target encoding, which I'm not going to go into detail, but that's like a really nice way to handle these like difficult categorical columns that you might find in your data. Okay, so this is our approach basically. And the reason these two things work well together is because stacked ensembles perform really well if the individual models in the ensembles are relatively strong, and also that they make uncorrelated errors. And by that just means, they fail in different ways. And so it's nice that you have kind of a variety of, this is just sort of intuitive really. Like if you have a diverse team at your work, like you're gonna have better approaches to things, because everybody has different experiences and different skill sets. So if you're given a new problem, like maybe one of the people in the group is really good at that problem, and maybe on another problem somebody else is, and it's really just the same thing with machine learning. And so we find there's a lot of analogies to real life here. So so one of the reasons that random search works well is because it kind of, when you're randomly generating models, that's a great way to create diversity in the model set. So not only do we get diversity from just having different algorithms like GBM, random forest, deep neural nets, GLM, But within that, we have a wide variety of GBMs that we've generated randomly. So we get a lot of diversity, and that helps the stacked ensemble do a good job. Okay, so this is the, kind of just the overview that I've just detailed, but this is kind of just to get you all on the same page. So basically the steps of the algorithm are we do some basic data pre-processing, dealing with, you know, missing data, categorical data, that type of thing. Then we train random, well, I say a random grid, but basically a random search across all of these different algorithms. So and we do that in kind of an order that we think makes sense. So we prioritize things at the beginning that we think are more useful. And one of the most useful algorithms that we have in H2O AutoML is actually XGBoost. And maybe second would be the H2O GBM. And you know, the deep neural nets are not usually doing that well, but you sometimes have a data set where that's really the best algorithm and then everything else does poorly. But in my experience, what I see a lot is XGBoost winning and doing a great job, and GBMs and maybe random forests after that, and then some deep neural nets and maybe GLM at the very bottom. And then we make sure, like I mentioned the automatic early stopping thing at the beginning. So we make sure that we don't overfit the models themselves. And then once we have, you know, once you say, run this for an hour and it has an hour's worth of models, whatever that is, it will train 2 stacked ensembles. So one is called the all models ensemble. And that's just what it sounds like. It's just an ensemble with everything in it. And then we have another ensemble that we create that just takes the best from each class. So the best GBM, the best neural network, the best random forest, best XGBoost, best GLM. I don't know if I missed one, but and the reason we have 2 is because we want to give you some options. So if you're trying to put a model into production, you probably don't want to put a 200 model stacked ensemble into production, because to make predictions with that model, you have to first make predictions on all the 200 models, and then you feed that into this secondary model, and then that gives you the final prediction. And so, you know, if you're not gaining that much performance by having that extra complexity, you could probably just go with a more lightweight one, and that's what we call the best of family ensemble. But if you really don't care about prediction speed or anything like that, then probably the all models stacked ensemble is going to be the best, and you can just use that. And then what you get back is you get this object that we call an H2O AutoML object. But one of the things inside of that that's, you know, probably the most important thing to look at is the thing that we call the leaderboard. And that's just essentially a data frame that has, as the rows, all the models that you trained and the model ID. So we just reference every model that has an ID so that we can refer to it later. And then it will have columns that represent the scores, like the cross-validated AUC, the log loss, the MSE. And I'll show you an example of that in a minute. And because, you know, you're just producing H2O models, all of these models, even if you don't choose the top one at the leaderboard, they can all be used, you know, in some way. If you want to export them to production, that's easy to do. And this is what the interface looks like. So yeah, that's pretty simple. You just basically import some data, and then you run this function and you tell it what your data is. H2O import file is basically like read CSV. It's just our function for doing that. So you tell it what your data is, you tell it what the column that you're trying to predict. You can also pass another argument if you want to remove columns, like if you have an ID column or something like that you don't want to use, then you can pass an X, and then X will say which columns you want to actually use as the predictors. Otherwise, it will just use everything that's not the response column. And then how long do you want it to run for? So you can say in terms of time, so max runtime seconds equals 600, means run it for 10 minutes. You can also say max models equals 20 or 50 or something like that. So you can, or you can use both together. So there's different ways of specifying how much work you want to do. And then you've got your leaderboard. And this is kind of a snapshot of what the leaderboard looks like. We have all of the models that were trained. So I asked it to train 20 models, and then it does 2 stacked ensembles at the end. So it just by default, like on a binary classification problem, will rank by cross-validated AUC. And we do cross-validation by default as well, and you can also turn that off. It does take extra time to do cross-validation instead of like a test set. You can pass a test set if you prefer the leaderboard to be on some other piece of data. But one of the reasons we do the cross-validation is that's required in order to do the stacked ensemble. So I'm not going to go into a whole lot of details, but that's one of the reasons why we do that. And so you just see the models there, and then once you look at them and you say, okay, I want to look at what is XGBoost_1, blah, 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 then you can just grab the model by ID. We have a function that's called h2o.getModel, and you put the ID in there, you grab it, and then you can look at the hyperparameters and explore it, and then just use it as if you were just to train it like in the console. Okay, so I don't have that much time, so I'm going to just skip through some tips here. One thing I'll just note is you don't have to use all the algorithms. You can turn them on or off. So if you don't want to use deep learning or you don't want to use GLMs or something like that, you can just turn that off. You can also use it just to tune a single algorithm. So you can tune everything off. We have exclude algos, but we also have include algos if you want to use that instead. So if you said include algos equals XGBoost, and then it would just do a big search on XGBoost and find the best XGBoost model. Maybe you could do XGBoost and stacked ensemble, and then it would create a stacked ensemble from your XGBoost. So you can use it however you want. We just, by default, do a wide search. And then the last thing I'll just say is, well, I'm going to skip over this, but basically, like, one of the things you have to think about in H2O is we are like meant to be a high performance, like scalable library where you're paying attention to things like memory and stuff like that. So if you need, I guess my recommendation here is like, just look at the documentation for h2o.init and it will tell you some more. But if you do find yourself like running out of memory, then you can just increase the memory using this argument here. I don't have time to go into too much about that. I'm gonna skip this as well so that we have time for questions. This is our roadmap. 2 things that I'm excited about that I'm working on are interpretability methods and algorithmic fairness methods. And I have a whole talk about that from UseR from Friday, which I'll give you a link to. I'm gonna skip this. How about we go for questions? If there are any, otherwise I can.
We do have one. Well, first, thank you, Erin, for a very, very comprehensive introduction to H2O and RML. We do have a question from Lisa Lanway. So her question is H2O something you would think about introducing to students, like in an advanced machine learning or data science course for undergrads?
Yeah, absolutely. I think that like we're headed in the trend of like a lot of people using these tools. So, you could learn it now or you could learn it in 2 years from now or whatever. But I think in particular, it's a nice intro library for new people. I mean, I use it myself. So I think there's a really wide range of, demographics of people who could benefit from this. But it's really an easy library for new people because you don't have to get stuck in the details of like hyperparameter tuning and all of that stuff. All you need to know is like the most important things about what is training data, how do you evaluate models, how do you like compare them against each other, and then how do you choose a model basically. And we kind of walk you through that as well. And it also forces you to like, it doesn't force you, but if you let it train all these different models, you start to be exposed to new models that maybe you're not familiar with, and you get to see how they perform on different data sets, and you start to see trends, and you start to look at the hyperparameters that are doing well, and then you start to maybe learn from that. So I feel like it's almost like a guided tool to get introduced to machine learning as well. So yeah, I think it's great to use.
So just one more very quick question before I hand this over to Lindsay. So we have another question from Charles Chen. The question is, how many algorithms are available in H2O?
I think there are maybe like 12 or 13 different algorithms. I don't have the full list in front of me, but some of the ones that we've added recently are SVM and GAMs, generalized additive models. So we're always trying to add like something new and exciting, like every big release. It's not always a new algorithm, but yeah, that's kind of our goal. So we do only add algorithms that do make sense to scale to big data. Some algorithms don't really scale that well, and so we don't deal with them. Or some are just not popular, so we don't add those either, unless somebody asks.
All right, thank you again, Erin. This has been great. And now we are going to move on to our next session, and I'm going to hand this over to our main organizer, Lindsay Dietz.
Thank you.